Welcome everybody to Business Math course. Today we're discussing rules of the derivative. This is Magda Talib Al-Hinay from Sultan Qaboos University and I welcome you all to our presentation. We start taking some rules of differentiation. The first rule is the derivative of a constant is equal to zero, and this we prove using the definition of the derivative as a limit. Of course, the c at x plus h is the same as having the same value as the c at x because it's constant everywhere. So we have that dc by dx is equal to limit as h goes to zero c minus c over h, which is 0 as we said. Next, we need to find the derivative of x power n, and here we are going also to use the definition of the derivative as a limit, as we're trying to reach that the derivative of x power n for any real number n is equal to n into x power n minus 1. So writing d by dx for x power n in terms of the definition as a limit, we have d of x power n with respect to x is equal to limit as h goes to 0 x plus h all power n minus x power n over h. We are going to use the binomial theorem to expand this bracket. We recall that a plus b all power n is equal to the summation from k equals 0 up to n of the binomial coefficients multiplied by a power n minus k multiplied by b power k. Again, we write the binomial coefficients in terms of factorials, and then we expand for the first three terms we see in front of us, that the first term is having a power n, and we expect the last term of the expansion to be b power n. Okay, now we apply the same thing up here for x plus h all power n. So we get limit as h goes to 0, and here we have the binomial expansion for the bracket x plus h all power n minus x power n. Now we see that there is a minus x power n and there is a plus x power n, so these two they add up to 0. So we have now limit as h goes to 0, and all the terms are having h in it in the numerator, and in the denominator we have the h. So if we look here, we have h power 1 and then h squared, and then h is everywhere until we reach h power n minus 1 and h power n. So let's think of taking h power 1 common factor, and we see what happens next. Yeah, we're doing this because if we plug in the 0, we'll get 0 over 0. So we're trying to cancel the 0 factor. So we take h common factor. We have here the h common factor outside. Now, why don't we just cancel the h in the numerator with the h in the denominator to get rid of the 0 factor? And here we go. If we apply the limit, we take the limit term by term. The only term which is not having h in it is the first term, and the rest terms, they will add up. They are all zeros, okay? So we get that the derivative of x power n is equal to n into x power n minus 1 as we wished. The following properties we are going to discuss on this slide are known as, together they are known as linearity property of differentiation. If we have the sum or the difference between two functions, we can differentiate it term by term. So the derivative of the sum or the difference is equal to the sum or the difference of the derivatives of two functions. So now let's prove this. We also start from the definition of the derivative as a limit. We take the left-hand side, we write d by dx of f of x plus g of x. We will prove it first for the plus, and whatever we're doing here, it's a similar thing you can do to the minus sign if we have a minus sign here. So the derivative of the sum of the two functions, we will apply the definition of the derivative as a limit. So this is equal to limit as h goes to 0, f of x plus h plus g of x plus h minus f of x plus g of x. So we're treating the whole thing as, one function, if we call it capital F of x. So here we will have capital F of x plus h minus capital F of x. In fact, capital F is the sum of f and g. All this divided by h. Now we will do the following. We will take the f's together and the g's together. We'll just rearrange the terms, and then we go on and split it into the sum of the f's over h plus the g's over h. So, and we split the limit, so we'll have for the first term limit as h goes to 0, f of x plus h minus f of x over h plus limit as h goes to 0 of g of x plus h minus g of x all over h. So, of course, this is the derivative of f with respect to x, and this is the derivative of g with respect to x, which is the property we are trying to prove for the plus. Similarly, we have this for the difference, and you can do it on your own following the same steps. Next, we take the derivative of cf of x, where c is a constant. This is equal to c df by dx. So as if we're taking the constant outside the differentiation sign. So now let's see how can we prove this. Again, our starting point will be the definition of the derivative as a limit. We will write d by dx of cf of x is equal to limit as h goes to 0, c of f of x plus h minus c of f of x all over h. Of course, we can take a c common factor and take it outside the limit. Now we are left with the c limit as h goes to 0 of f of x plus h minus f of x all over h, which is again the definition of the d by dx for the function f. So this is equal to c df by dx. Okay, now let's move on. Now let's see applications in this slide and in the coming one. We have f of x is equal to 15x power 100 minus 3x power 12 plus 5x minus 46. We need to differentiate this function. So we have to do differentiation term by term. Okay, so the derivative of f of x is f prime of x. We take the first term. We see that we have 15 times 100 x power 99 as a derivative of 15 x power 100. Now let's see the 3x power 12. It's here. Yes, it will be minus 3 into 12 into x power 11. We move on. Yes, 5x will be differentiated to 5 because it is 5 times 1 times x power 1 minus 1, which is x power 0, which is 1. Finally, we come to the derivative of minus 46. It is minus 0. So this will be the final form. We have 1500 minus 36, 1500 x power 99 minus 36 x power 11 plus 5. We move on to another example. Differentiate. Y equals cube root of x squared into 2x minus x squared. First of all, we will rewrite the form of y so that we replace this cube root of x squared by x power 2 over 3. In the coming step, we open the parentheses. So we have x power 2 over 3 times 2x is this 2x power 5 over 3 minus x power 2 over 3 times x squared, which is x power 8 over 3, and the minus sign, of course, as it is. Next, we differentiate, so we put down the power. So we have 2 times 5 over 3, which is 10 over 3, x power 5 over 3 minus 1, which is x power 2 over 3. For the second term, we have x power 8 over 3. It will be differentiated to 8 over 3 x power 5 over 3. Now we move on to the coming slide. We continue our. Here we come to another example. We have h of t equals 2t power 5 plus t squared minus 5 all over t squared. We're going to differentiate this term by splitting this whole fraction into the sum of three fractions, the denominator of which is t squared. So we have each of these fractions is having a t squared in the denominator, so we have 2t power 5 over t squared plus t squared over t squared minus 5 over t squared, and we cancel the t squared with the t power 5. Also here we cancel the t squared with the t squared. So we are left with h of t to be equal to t cubed plus 1 minus 5t power minus 2. And we differentiate term by term. The derivative of the first term is 6t squared and the derivative of the second term is 0. We're not going to write it. And for the third term, we have a minus 5. When we differentiate the t power minus 2, we will get a minus 2 times minus 5, which is plus 10. T power minus 2 minus 1, which is t power minus 3. We move on to see the coming example. Differentiate g of t is equal to 4 into t plus 1 all squared into t minus 3. In order to perform differentiation, we need to open the parentheses. We start by squaring t plus 1. So we will have 4 into t squared plus 2t plus 1 multiplied by t minus 3. And then we open this bracket by multiplying term by term. For the first term, we have t squared times t, which is t cubed, and then 2t squared, and then t. Next, we multiply by minus 3 term by term. We will have minus 3t squared minus 6t minus 3. And then in the coming step, we add the like terms, so we will get this simplified reduced form. 4 into t cubed minus t squared minus 5t minus 3. Next, we multiply term by 4. We have 4t cubed minus 4t squared minus 20t minus 12. Now we differentiate term by term to get the g prime. The derivative of the t cubed is 3t squared. The derivative of the t squared is 2t. The derivative of t is 1, and the derivative of the constant is 0. So here we will have 4 times 3 is 12t squared minus 4 times 2, which is 8t, minus 20, and this will be the derivative we are looking for.